Down in the darkest depths of the ocean, a violent chemical clash happens every day. Glowing magma, burning at over 1,000 degrees Celsius, erupts directly into near-freezing seawater. This is actually the norm for our planet. Roughly 3/4 of all volcanoes on Earth sit not on land, but hidden 1 to 4 kilometers below the ocean surface. Basic intuition suggests that dumping thousands of tons of molten rock into freezing water should simply trigger massive steam explosions. Some climate skeptics have even claimed this intense deep-sea heat is what's melting the polar ice caps from below. We can see where this extreme clash happens by looking at this bathymetric map of the Gakkel Ridge in the Arctic Ocean. It's an ultra-slow-spreading ridge where magma routinely breaches the Earth's crust directly beneath the ice. So how do these two extremes physically touch without neutralizing each other, boiling the sea or melting the ice above? The answer comes down to physics. The ocean actually defends itself using a 3-layered physical shield. The first line of defense happens exactly at the microscopic point of contact, the very millimeter where hot magma meets cold seawater. When that contact occurs, the water touching the magma vaporizes so quickly that it triggers the Leidenfrost effect. This steam film acts as a thermal blanket, which we can see on this chart mapping heat flux against temperature difference. Notice the sudden plunge into the section labeled film boiling. Following the curve down, heat transfer hits its absolute lowest point precisely when the vapor film forms at TL. This intense heat actually prevents immediate vaporization, buying the system time and ensuring the ocean doesn't boil on impact. But occasionally, that vapor film collapses, and the volcano attempts a massive explosion into the water column directly above the vent. This triggers the second line of defense. At depths of 1 to 4 kilometers, the crushing hydrostatic weight of the ocean physically suppresses the explosive expansion of volatile volcanic gases. Even when an ash plume does manage to erupt, the physics governing it operate completely differently than they do on land. Deep-sea plumes experience something called negative buoyancy. As the hot plume tries to rise, it rapidly sucks in massive amounts of the surrounding freezing seawater, instantly cooling the entire column down. Because of this rapid cooling, the plume quickly becomes too dense and heavy to rise. It loses upward momentum and collapses right back down onto itself, flattening out just tens to hundreds of meters above the seafloor. The immense pressure and extreme thermodynamics of the deep ocean physically trap the eruption's destructive energy exactly where it started. Zooming out from the vent to the macro scale, we can look at the entire Arctic Ocean as a single massive physical body doing the rest of the work. The ocean itself acts as a giant heat sink. Because water has a thermal conductivity roughly 20 times greater than air, it can readily absorb and rapidly disperse ambient heat. But the ultimate barrier is ocean stratification. The Arctic Ocean is layered like a cake, organized strictly by physical density. The bottom layer is the coldest and saltiest, making it the densest, while the upper layers are warmer, less salty, and lighter. Because these waters differ so wildly in density, they rarely mix. The freezing, salty water at the very bottom remains trapped there. When volcanic heat attempts to rise, it hits the boundary of this dense lowest layer and disperses horizontally, physically blocked from transmitting into the layers above. Thanks to this macro shield, practically zero heat from these 3,000 to 4,000 meter depths ever bridges the 2.5-mile vertical gap to reach the underside of the surface ice. Back on the surface, directly above these enormous 1,000-degree eruptions, the water remains perfectly calm and locked in ice. This physical reality leaves absolutely no merit to the claim that deep-sea volcanoes are causing recent polar sea ice melt. The ocean flawlessly absorbs and contains this massive injection of thermal energy, managing volatile gases through its own structural physics. By trapping the heat and slowly leaching minerals into the deep water, this intense temperature clash dictates deep ocean chemistry. It sustains entirely unique, lightless ecosystems at the bottom of the world. This deep-sea clash is a masterclass in planetary engineering, a testament to the insulating, life-sustaining power of Earth's oceans.